there's a chair there. Let's go ahead and do example 1 again. I know we did it yesterday, but you will have questions like this on the exam as well. So let's just kind of look at them again. It's a new day, right? It says to simplify the following radical expressions by combining like radicals. So we have the square root of 32 plus the square root of 200. Those are two terms, and we can only combine them when they have like information in them. And in this case, it's probably going to be like radicals. So they're both square roots, but neither one of those numbers in the radical or under the radicand, are perfect squares. So do they have factors that are perfect squares? The answer is yes. Yesterday, we just went right to it. 32 is 16 times 2. But what if you're not sure if it has a perfect square factor? How would you do it? What's that? You can write out the factors. So you could do your factor tree. Remember doing factor tree? Let's see. It's going to be 2 times 16. That's 2 times 8. That's 2 times 4. And that's 2 times 2. So here's the prime factorization. It's 2 to the 5th, right? Here's what's nice about radicals. What's the implied root index if it's square root? 2. I'm going to go ahead and write it in there. This root index tells you the price or how many factors of one type on the inside of the radical you need to become 1 on the outside. So a pair of factors on the inside can become 1 on the outside. So here's what you could do. You could say, in general, I have a pair of 2's. So there's a pair, so I could bring one of those out front. I have another pair of 2's, so I can bring another factor of 2 out front. And then I have this odd 2 out that's left, so that'll just become the square root of 2. So that's one way to do it. And, of course, that becomes what? 4 square root of 2? You can also just say it's 16 times 2, and the square root of 16 is 4. If you don't want to do factor trees, let's say 200, you didn't realize it was 100, you could do the upside-down birthday cake. Remember that? There's 200. 2 goes into it, that's 100. 2 goes into it, that's 50. 2 goes into that, that's 25. There's 5, that gives you 5. 5 goes into itself once. And here's the prime factorization, upside-down birthday cake. Kind of works the same way. Well, one more time, you could say then a pair of factors on the inside becomes 1 on the outside. So plus, let's see one more time. We got a pair of 2's, so I could bring a factor of, bless you, 2 out. I have a pair of 5's, so I could bring a 5 out. And what's left? The 1 doesn't count because it's 1. I have a 2 left, right? So that's going to stay under the radical. So in general, that's how you can split things up. So now you have 4 square root of 2 plus 10 square root of 2. And now we have like radicals. 4 of those plus 10 of those equals 14 of those. And you're done. Yep. All right, does it work the same for fifth roots? Sure does. Does 96 have a perfect fifth root? I don't know. Okay? There's 2 ways you can figure it out. The fifth root of 3, that looks like it's irreducible. So I mentioned yesterday that probably means that this first one's going to be written as the cube root of 3 with the coefficient out front, which means 96 is probably going to be 3 times something. But let's say that we didn't realize that. Let's do upside down birthday cake, because who doesn't like cake? Let's factor 96. You got a 2, and that's going to be what? 48. Good. And then 2, that's going to become 24. Another 2 gives you 12. Another 2 gives you 6. Another 2 gives you 3. And then if you want to keep going down the side, you get a 3 and a 1. So if you keep going all the way to a 1, you have your prime factorization down the side. Now, what's the price to get out of the radical? It takes how many factors of one type? 5. It takes 5 factors of one type on the inside to become 1 on the outside. So we have 1, 2, 3, 4. We do have 5 2's. Yay. So those 5 2's on the inside become 1 on the outside. Do I have 5 3's? No, I just have 1. So anything that's not in groups of 5 remains under the radical and gets multiplied back together. In this case, it's just 3. And I'll put a 1 fifth root of 3. And then 2 of those plus 1 of those makes 3 of those. So there it is in simplified radical notation. Now we could do one other thing here, because that's a 3 fifth root of 3. That's 3 to the first times 3 to the 1/5, right? And we can write that as what? 3 to the... What's 1 plus a fifth? 1 is how many fifths? 5. So 5 fifths plus 1/5 is 6 fifths. That's another version of it. Okay? And of course, that would be the fifth root of 3 to the 6, but so on and so forth. This would be the simplified radical version of it. All right, so now you know factor trees upside down, birthday cake. All right, let's look at these real quick. Simplify by rationalizing, kind of like what we did in the warm-up. Rationalizing simply means getting rid of the radical from wherever it currently is. If it's in the denominator, we're going to get it to the top and vice versa. The first thing you want to do, though, is simplify your radical. Is the square root of 3 simplified? Is it? Yeah, it's not a perfect square, nor does it have a factor that is other than 1. So in this case, we're going to multiply by a clever form of 1, which is radical over radical. What does multiplying by 1 do to the expression? What's anything times 1? Itself. So it doesn't change its value. So we get 2 square root of 3 over 3, like we said before the warm-up. And you're done. All right, let's look at this one. Square root of 12 over 4. We're going to rationalize it. What did I say the first step was? Simplify your radical. Does the square root of 12 simplify? It does. It's not a perfect square, but does it have a factor that is? 4, right? It's 4 times 3. So that becomes, if you want to do it in slow motion, the square root of 4 times 3. You can write it like that. And of course, the square root of 4 becomes 2, so you get 2 square root of 3 over 4. Whew, I broke a sweat. I'm done. Are we done? Box it up, walk away? No, the task was to rationalize it. So I need to get the radical out of the numerator. All I've done is I've made the work a little bit easier on the front end than having to simplify so much on the back end. So to get rid of the radical on the top, I'm going to multiply by a clever form of 1. What do you reckon it's going to be? Square root of 3 over square root of 3. You don't have to get the 2 involved. Just square root of 3 over square root of 3. Now we multiply straight across, and we get square root of 3 times square root of 3 is what? Well, square root of 3 times square root of 3 is the square root of 9, which is really 3. Because remember, it's 3 to the 1/2 times 3 to the 1/2, which is 3 to the 1st. So you get a 3 times 2, which is 6, all over 4 square root of 3. Now we're done. Simplify early and often. This would be the often part. There is a common factor of 2 that you can divide out, so it becomes 3 over 2 square root of 3. And you're done. We rationalize the numerator by getting the radical into the denominator and eliminating it from the numerator. Okay, now this one here is kind of interesting. I have a radical in the denominator. I want to rationalize it, which means I want to get rid of the radical from the denominator and move it to the top. So, what do you think we're going to multiply by? Cube root of x squared over the cube root of x squared. That's a very likely assumption because over here, if I had the square root of 3, I just multiply by itself. But look what happens if I do that. If I put it in fractional exponent notation, I get x to the 2/3 times x to the 2/3, x to the 2/3, right? What do I get in the bottom? When I multiply, I add the exponents. What's 2/3 plus 2/3? 4/3. Is 4/3 still a radical in disguise? Yes. So it doesn't work necessarily just to multiply by the radical repeated. What are we trying to accomplish? To get rid of the radical, I'm essentially trying to make the fractional exponents what? The only way we're going to get rid of a radical is if the fractional exponent is gone, right? So you have to make the fraction whole. And that's why it worked over here. This is 3 to the 1/2 power. How do you make a 1/2 whole? You need another what? Another half, don't you, to make it whole. So over here, if we're really starting with an x to the 2/3, what do we need to make a 2/3 whole? A 1/3. So you would multiply by the cube root of x or the cube root of x, or x to the 1/3 over x to the 1/3. So that's a little bit of insight. We're trying to make the fractional exponent whole. So cube root of x over cube root of x. Now let's see what we get in the bottom. What's 2/3 plus 1/3? 3/3 or 1. So we have x to the first, and on the top we have 2 cube root of x. And there's the answer. So that's how you rationalize. You're making fractional exponents whole. Now you've probably only had limited experience with square roots, which is why you maybe thought you just multiply by the same radical. All right, I'm going to skip D, and let's go quickly over here to E. It looks like it's been graffitied. In light of our warm-up, this is going to be a piece of trail mix now, right? Anyone put cake in their trail mix? I don't know if that's ever been tried before. Just saying. That'd be good. What do we multiply by, guys? I can't just multiply by square root of 2 over square root of 2 because I have two terms. So I have to multiply the, what's the word? Conjugate. So it's going to be 3 plus square root of 2 and 3 plus square root of 2, right? Because we're just multiplying by a clever form of what? 1. Now, the expansion should always take place with the conjugates. Always expand the conjugates. Always. 3 times 3 is 9. The inside and outside will cancel. Minus 3 root 2 plus 3 root 2, boom, gone, 0. And then you have negative square root of 2 times positive square root of 2, which is negative what? Negative 2. Square root of 2 times square root of 2 is just 2. Negative times positive is negative. In the top, leave it factored. You only want to expand the conjugates. Why would you want to leave it factored in the top? So that possibly you can divide out common what's? Factors. So leave it factored in the top. But by design, we expand out the conjugates to get rid of the radical. So what's really in the denominator? A 7. That's worth a whole other line of writing. And then what happens with 14/7? It reduces. They divide out to give us a 2. And you got to make sure it's still in parentheses. So you could stop right there, or if you want to distribute 6 plus 2 square root of 2. Either one of those are fine and dandy. Okay? So multiply by the conjugate. And as we saw in the warm-up, you want to leave the other side factor. If it's not factored already, factor it out. Okay. Picking and choosing. We're going to save complex fractions for the next test. So that monster right there, we'll just wait. And this guy here, we'll wait. All right, evaluating. Pretty easy, right? Evaluating. Let's look at example 4. If I give you f of x equals this, function notation means whatever this x is here, you're going to plug it in for this x and this x, right? So you could think of it as f of blob is equal to 3 blob squared plus 2 blob minus 4, right? Or f of blue unicorn is equal to 3 blue unicorn squared plus 2 blue unicorn minus 4, right? Or f of trail mix is equal to 3 trail mix squared plus 2 trail mix minus 4. It doesn't matter what this x is here. We're going to plug it in both places there, right? We're going to square it once and not square it the other time. So let us evaluate the function at -2. Okay? Now this one should be easy, but let me tell you before you even start that here's what I would recommend doing. This squared can get kind of tricky. You're multiplying it by itself and then times 3, and this one over here, you're multiplying it by 2. Here's what I would recommend. Everywhere you have an x, when you're plugging in, do it like this first. In place of x, put a receptacle, an open set of parentheses. It's almost like going backwards from algebra. When you first learned algebra, you didn't have x's in there for missing things. You had like boxes or a blank. And the teacher said, fill in the box with a blank. We're kind of doing the same thing. We're putting parentheses. Now, step 2, whatever is in here for x, in this case -2, you're going to drop in here to the parentheses as a second step. Why would that be beneficial? What would that eliminate the possibility of doing? Careless mistakes with order of operations, okay? Now, I recommend doing this. Some people decide that they don't want to do it, and guess what? If you get it right, that's fine, but a lot of people don't do it this way, and they get it wrong. Don't do that. All right, so now your dear Aunt Sally says to square the -2. What's -2 squared? 4. 4 times 3? 12. And then 2 times -2? -4 minus 4. And what do we get? 12 minus 8 is 4. Yeah, there's the answer. Okay? All right, h of f of x. We have h of x equaling this. That's how we read that. That's h of f of x. H of f of x. That's not multiplication. What this means is we are plugging in the f of x function for x into the h function. So here's the h function. So here's how this one's going to be. This is going to be equal to 5 minus 4 input, or blob. So I'm going to go 5 minus 4 blob. And what did I put for my blob or my x? Parentheses. And what am I going to plug in for x? f of x, right? The entire function f of x, which is 3x squared plus 2x minus 4. 3x squared plus 2x minus 4. So notice the parentheses are there to avoid a mistake. This is not multiplication. That's h of f of x. You're plugging f of x into the function h for x. And then, of course, if you want to distribute there, 5 minus 12x squared minus 8x plus 16, you could then collect like terms. Let's do that. That's negative 12x squared minus 8x, and then you get plus 21. It's not multiplication. It's composition. Now, that's one way to write h of f of x. You can also write composition like this, and I'm sure you've seen it, like fog or golf. This one's faux. This open circle does not mean multiplication. It means what? Of. It's like the O in of. So this also means f of h of x. Now, this is the condensed version. If you want to write it the other way, that's the same as f of h of x. And I kind of prefer that version because this one's a little bit more intuitive, right? Because you can physically see that the h of x function now is being dropped inside the f function. So you start with the outside function, f. Now f is back over here. What is it? It's 3 blob squared plus 2 blob minus 4. So let's do that. Let's set the table. 3 blob squared plus 2 blob minus 4. That's my first step. I replaced x with parentheses, step 1. Now step 2, I'm going to come back, and in my parentheses, I'm going to drop what? H of x. Now I'm not going to put the name h of x. I could, it wouldn't be wrong, but h of x is equal to 5 minus 4x. So wherever I have a parentheses, 5 minus 4x, 5 minus 4x. And I've set it up correctly now. It's 3 blob squared plus 2 blob minus 4, and my blob is a binomial. All right, let's go ahead and expand this out, because this is no mean feat right here. I have 3 times the quantity squared. Do you remember I told you the other day how we're going to quickly square a binomial? You don't want to just square the first and square the second, and you don't want to have to go off to the side and write them side by side and FOIL it. So square, multiply double, square. Remember that? Square, multiply double, square. So if we square 5, we get 25. You multiply and you get negative 20x, and double it to get negative 40x. And then you square the last. Negative 4x times negative 4x is positive 16x squared. And I use brackets there. Notice you still have to distribute the 3. Parentheses will work well. Square, multiply, double, square. That's how you expand a binomial. This you're just distributing. So plus 10 minus 8x and then minus 4. Distribute the 2 and then minus 4. Now I can distribute the 3, right? 75 minus 120x plus, it's going to be 54x squared. And then I can go minus 8x, and then 10 minus 4, you can combine those to get plus 6. Wow. Now, the last thing I'll do is organize, collect like terms, and write it in descending order. I got a 54x squared. I got a negative 120 and a negative 8x, so negative 128x. Then I got a 75 plus 6, which is positive 81. Yowza. Now, we're not going to try and factor that. Okay? Maybe this weekend we can. Got it? This is composition. We're plugging one function inside another. We're putting parentheses in place of x first, and then a second step, we're coming back and plugging in. You would be surprised how many people can't even get it set up correctly. There's my website. Sure. All right, looks like I lost my connection.